Yes. All right. So my name is Nathan Wikmann. I work at Cray back in the performance analysis team in Minnesota. I do a lot of different things, wear a lot of different hats about benchmarking and whatnot. Today I'm going to be talking about the XC30 system in general. That was previously codenamed Cascade. So if you hear me say Cascade, I'm talking about the same system here. It is a lot about the network, so we're going to be spending probably a little bit more time on the network. And the network is quite different than anything out there before. So feel free to stop me, ask questions. The more lively this group is in asking questions, the more fun it is for me and for everyone else. So don't hesitate to interrupt me or challenge me on a couple of points. Jeff said that he was going to try, so we'll see how he does. We're going to start off today talking about the Aries custom interconnect. It is custom. We do the network ourselves. We do the network ASIC ourselves. And then all the fabric is our own fabric as well. Why are we doing this, and what is the difference between Aries and Gemini? Gemini is the router chip that is in the XE30, the current production science machine here, and the product that we've been shipping now for several years. Well, the main differences are a 3x increase in the sustained injection bandwidth. So we're changing the technology. Gemini was based off of hypertransport. This is now moving towards a PCI connection, and it actually provides better bandwidth in general, going across a range of applications. We have also, the next thing is a very large increase in global bandwidth. This will be a theme on a couple of things this week. The Gemini system was a 3D torus. It was good in a lot of ways for bandwidth, but 3D torus don't necessarily scale quite as well as some people like in terms of global bandwidth if you're doing an MPI all-to-all across the machine or whatever. And so this actually provides a massive increase in global bandwidth. Now we'll give a range because really the exact increase depends on the size of the machine and in configurations and whatnot. But it is really going to benefit codes that do all-to-all, do searching, adaptive mesh refinement, higher order nearest neighbor, the 3D and 4D type of nearest neighbor codes. If your codes do a lot of communication, that's where it's going to see some benefit. We also have support for some collectives, barriers, and all reduce. Okay. That's okay. Yeah, funny faces. Over to my right is the entertainment, right? So we do have some hardware support for collectives. This will speed up a few things about barriers and all reduce if you do those with the really high frequencies. The interesting challenge there is that many times when we see barriers taking a long time, we're always going to ask ourselves, is it because the barrier is taking a long time, or is it because there's some type of imbalance in the code, and it's whoever is getting there last is the result to what's causing it to take a long time? So that's going to be an interesting thing to watch. We do increase the size or the rate at which we do small messages. If you go way back in history to the machine previous to Gemini, actually, that was pretty good at some things, but it actually was pretty poor at message rate. We had a massive increase in small word message rate going from that machine to Gemini. Well, so we didn't need as large of an increase going from Gemini to Aries, but we still improved it, in this case, by about 3x. And then the PCI is our new interface to the processor. This benefits us because it makes us less dependent on processors going forward. They should be able to connect up to anything that talks to talks PCI in the future. So really the philosophy behind the network is we use the right mechanism to transfer bits at the right level for the cost. We're optimizing cost in terms of, well, if we're transferring it over this distance, this is the best way to transfer the bits. And so starting at the left-hand side, we have this concept of what we call a rank 1 network. The rank 1 network is communication through a PC board. And I don't know really what the units are, but the point is that you're transferring it for pennies. It's really relatively cheap to lay down wires and to get bandwidth over this level. Now, a PC board, you can't build a PC board that spans the machine room. This is the size of what we call a chassis. So something less than a meter is the distance that this is transferring data over. The next level is what we call a rank 2 network. Passive copper is what that is. Now, copper is really good in a couple of regards. You can have pretty good signal rates in it. It is really relatively cheap, but the cables themselves are really pretty thick, and they don't go very far. Those are the two cons. In this case, we're talking a few meters in distances where they really can live well without needing repeaters or slowing down. So the rank 2 network is using passive coppers to communicate between cabinets. And the total distance, I think, is going to be something on the order of 3 meters or less by the time the cables are coiled around. Then we have a rank 3 network, and that's active optics. Active optics, fiber optics, what's being transferred is light. This is a very low latency, no matter the distance of the optics, and the cost of the optical cable itself is not strongly dependent on the distance it needs to go. So this really frees us up to have cables that are very long. The thing that makes it the most expensive, though, are the endpoints. They cost more. The actual endpoints cost more to hook up to machines and to get the bit rates that we need. So it is something that we don't want to use throughout the machine, but we want to use it where it has its advantage, and that is communicating between what we call groups, communicating between pairs of cabinets. And furthermore, the number of optical cables that you can get in an XC30 is actually dialable by the site. You can choose to connect in more or fewer. So that's going to help us optimize the cost of the system, so you're kind of putting the money where you want it. If it's in the network, if it's in a global network, you can buy more optical cables, or if you don't think you'll need that many, you can buy fewer, and that'll free up money to buy more memory or more boards. We'll go into differences in speed and bandwidth, but the signaling rate of this is a little bit higher than the signal rate of these, but we'll actually see, hopefully, at the end of today, really what matters is not the speed of an individual cable, but the speed of the aggregate system. So these are our building blocks. We start with a compute blade. A compute blade has actually 4 compute nodes on it. Each compute node has 2 sockets. We'll talk about a compute node in a little bit. But this is really the smallest physical unit that goes into the system. They all connect up to one Aries card that then communicates with the outer world. We put 16 compute blades together into one chassis. And this is pretty densely packed when you get it all together. And they all plug into one backplane. And you can, this is an engineering diagram, but nonetheless, you can see this green-black backplane. That is the rank 1 network, and that's what implements the rank 1 network, which we'll talk a little bit more about its topology in a moment. Once you have a full chassis, you put multiple chassis together, 3 in one group, and then three in one chassis, 3 in another chassis, to form what is called a group. Now, that group is tied together with the rank 2 network that I talked about, passive electrical network that where the cables are basically running between the chassis. All total, by the time you get up to 2 groups, that's 384 compute nodes, 700 and some sockets, right? Now, a rank 3 or a full system is cabled together with the rank 3 system. If we have the opportunity, hint, hint, to go upstairs and actually look at see the system through the window, you'll actually see it. It looks very similar to this, different picture on the front, but there are going to be kind of pairs of cabinets that make up a group, and then there's going to be multiples of these in a row, and then there's another row behind it. All of the communication that's happening between these pairs is going across the optical network. So slide 6 and then slide 7. The compute blade architecture basically is in many ways very similar to the XE system. We have our Aries chip represented here with a picture of a dragonfly on it that is connected to one of the Intel sockets via PCI 3. It's a 16 bits at 8 gigatransfers per second. That's a hardware type of limit. We'll talk a little bit later about what we practically see going across that. But that connects to one socket, and then that socket is connected to another socket on the same node via what they call QPI links. This is the standard QPI connections that actually is how you hook up multiple sockets in any Intel-based system. These two are actually quite fast in terms of bandwidth, at least. So you can really, for large messages, get the same bandwidth off the far socket as you can get off the near socket. These sockets, each socket is directly attached via 4 channels of DDR3 to a local memory. So if you're in this socket, ideally, if you're running on one socket, ideally you're using the memory attached to that socket. If your processor is running on the other one, you're using the memory attached to that socket. And that happens naturally if you're just placing an MPI job on the system and spreading it across both sockets. That happens pretty naturally. It only becomes really something you need to think about if you're going to do a shared memory parallelism that really is larger than than any one socket. So inside the socket, Intel is coming here tomorrow. They'll probably talk a little bit more about it, and even if they don't, I'm going to talk even more about some of the speeds and feeds of a Sandy Bridge. But for now, I'm going to say that inside one socket, there are 7 cores, okay? And each core has its own L1 and L2 cache, and then the 7 cores share a 20 megabyte L3 cache. All 7 cores have equal access to the level 3 cache and equal access to the memory. So this really becomes a natural, some people say NUMA domain, some people say UMA domain, uniform memory access between these 8 cores to the cache and to the memory. I think it's a natural place where programming environment, programming model like OpenMP or pthreads lives. That's the most natural extent of it, or some integer that divides evenly into 8. That's a natural place where it's gonna fit. So moving on into the compute blade, then you can see that for our compute blade, you saw a small picture of it before, but here we have actually 4 compute blades that are all hanging off one Aries chip, and each complete compute blade, 4 compute nodes that each hanging off I get screwed up on my own terminology, right? Each hanging off of one Aries. It's for a total of 8 sockets. Basically, if you end up communicating from one compute node to another compute node on the same blade, the data gets shot into the Aries, gets scrambled around, and gets shot back out. I would actually say it technically never goes on the network. It never gets transferred across any kind of the rank 1, rank 2, or rank 3 routers or wires, right? So that communication is pretty fast, pretty direct. But at the same time, you don't really think about is your node on the same blade or not. It's just an interesting, this is how things are physically put together if you ever see a diagram. So the Aries is a 48-port router. It actually has 4 NICs. You know, a NIC is network interface card. It's not a card anymore. It's just a tiny piece of silicon on a larger piece of silicon. It's shrunk down that much. But it's 4 NICs. Each NIC communicates with one of the nodes. And then there's actually internal, there's 40 router tiles. And that's what actually implements the routing scheme and the scrambling of the messages and spitting them back out towards their final destination. These are just the same things I said before about QPI links and 4 DDR channels to memory. The next box here is coming out of Aries. We represent it as one big pipe, but actually there's lots of different wires that implement the chassis level. I will actually say green network. That's the name we've given the rank 1 network for a long time. We actually call them green, black, and blue. And the story is that the first time it was drawn on a whiteboard, they had green, black, and blue markers, and the names stuck. So if you ever hear me say green, black, and blue, that's what I'm referring to. The green is the rank 1 network. It's the back plane. It's easy to remember because the back planes, most of these PC boards are actually green. The next level is coming out of the same chip is black, and those are the copper cables, the rank 2 network. Again, most blacks they're surrounded, most copper cables are actually surrounded by a black shielding. So that's another way to think of that one. And then the blue network is the opticals. All 3 of these are coming out of a single Aries. So an Aries it's every single Aries, for all practical purposes, every single Aries is attached to all 3 of these networks, and it can choose to send a packet, which is a piece of your message, in any one of those, depending on its final destination or depending on the conditions on the network. So there's a little bit you can also see. This one's running at 14 gigabits a second, 14 and 12. So the optical is running technically a little bit slower in terms of signaling rate, but we don't worry about the signaling rate of an individual wire too much because the way Dragonfly works, it's really the aggregate that matters more. So when we fully populate a blade, this is a blown up picture of what you saw before. This little cartoon here on the upper right-hand side of slide 9 is what actually looks like in physical reality at the bottom. So you can see the heat sinks associated with the different processors. Each heat sink represents one socket. In between, you have the memory cards and other heat sinks for various controllers and whatnot. They are actually all communicating via the Aries chip right over here, which has the heat sink off of it. They're communicating through PCI ribbons is how they actually go across. So communicate to the Aries. This Aries then has connectors that these connectors, I can't remember which one is which, but the connectors plug into the backplane and it will make the connections to the green, the black, power, and then I think one set is also the optical connectors that they plug into the optical optical network, global network. So this is then our I/O module. Really inside the system, inside the whole fabric, is what I've been describing so far, the compute-only blades. This is where your main application runs. But if it wants to communicate, or it wants to communicate with the outside world, if it wants to save things to the files, we need a blade that's designed to hook up to a file system. And there are blades like this. You're probably not in, you will never be, need to know the internals of this blade too much. But it's interesting to note that this blade is actually relatively similar to the other blades in that it's got an Aries card. It's got an Aries router chip right there. It plugs into the same fabric, so it's got the same access as every other blade in the system. And your data gets transferred across the high-speed network to this endpoint. It has 2 Sandy Bridge processors on it. Actually, that's the only processors that we have. We just put in baffles on the other ones and placeholders because they wouldn't be doing anything. I think they actually, if you would try and put it in there, it would slow things down. But you don't want to design a whole nother board, so it's just cheaper to put in placeholders there. And then PCI card slots. This is where your InfiniBand or other fabric with the outside world it plugs in. Okay? This is an I/O module, input-output module. Yep. And not a login module or anything like that. It just is what's interesting. If you ever see a diagram of what the machine is, you might see something that's called S's in there and stuff. Those are service blades. But it's interesting to note that when you're communicating through the outside world, your data is actually transferred across the high-speed network first to an I/O module, and then at the I/O module, it gets sent out to the rest of the file system or gigabit Ethernet or whatnot. And there's multiple of these in any system. So next we're going to talk about the Dragonfly topology. And this is something that I often say you kind of see it once and you think about it a little bit and you walk away and it might have been a little bit confusing and then you come back to it but hopefully we're getting we'll set the basis for okay, I can sort of think about how this machine is built and do I need to worry about it or don't. And like I said, by all means, if you have questions, go ahead and stop me and I can back up and explain it. It will be useful to everyone. So this is a picture of the rank 1 network. Okay, up in the right-hand corner, this is our chassis with 16 blades hooked all into the same PC board. 16 blades. Each blade has 4 compute nodes. So this is 64 compute nodes. This is quite a bit of compute power by itself that's represented in this chassis. Now, the way it works is that every single Aries in every single blade has a direct connection to every other Aries in the same chassis. It's an all-to-all connection. And it's got one and only one connection between every Aries. That's our picture on the left here, slide 12 for those that are following along. The question becomes, well, what happens if I send a message, say, from the Aries in slot 3 to another Aries in the system? And we have a red dot that's associated with that message. So if I'm in slideshow mode, you won't see this in PDF, but if you're in slideshow mode and I click, you're going to see a red dot is shooting from Aries in slot 3 to the Aries in slot 11. It can go across that direct connection between those two things. But when I send a message that's anything larger than 64 bytes long, okay, the hardware actually takes that message and chops it up into packets. And so your larger message is chopped into a number of packets. And then it's possible that actually it's very easy that the direct connection is overwhelmed with the number of packets. So the Dragonfly network is designed to bounce additional packets off of additional Aries. And in this case, we see this by, we still have the direct connection, the red line going from slot 3 to slot 11. But we also have it, another dot that's bouncing off of slot 14. And it can do this adaptively. If like I said, if the direct connection is overwhelmed, it starts bouncing it off another Aries. And it bounces off not only one other Aries, it can bounce it off multiple Aries. So we hit it again, and now we're bouncing it off slot 7, slot 14, and directly going to slot 11. Now, this doesn't even represent what's really going on, because this implies, well, once it bounces off 7, it keeps bouncing it off 7. No, every single packet can take a different path. It doesn't really matter, and it will. You can think of it as when it's in this mode, is it basically bounces it off other random Aries. So it could bounce it off one packet off of 14, one packet off of 15, the other off of 9. It all doesn't matter. So remember, you kind of asked about what's the speed of a wire. Well, the speed of a wire doesn't matter. It's the speed of all of the wires in the system that begin to matter, because it's very easy to overwhelm the wire in between, but it's not easy, and it's almost impossible to overwhelm all of the wires in this system simultaneously. So now we're going to look at the electrical network. That was, the previous slide was the PC board network, right? And now we're going to look at the electrical network. We're going to build up from the ground again. Down in the bottom of slide 13, we have our 4 nodes connected to one Aries. We'll hit the button one time, and inside this yellow box, we actually have 16 Aries, all connected through an all-to-all represented by this bunch of green lines here. Every Aries is connected to every other Aries in that green network back plane. Click it one more time again, and in the gray box, we actually have 3 chassis. So this is one cabinet, right? One cabinet fits 3 chassis, all in there. Well, we have to click it again to have 2 cabinets as forms our group, what we call a group. So now we have 6 chassis physically in 2 groups, but the important thing is we have 6 chassis. And how do I get from one chassis to another chassis? Well, that is where the electrical network comes in. Now, running vertically between Aries, which I will say is in a column, is an all-to-all network implemented with these black cables. So every Aries in a column has a direct connection to every other Aries in the same column. Not every Aries in the group, but every other Aries in the same column. So you can kind of see, well, already, and this is going to be in a couple of slides, but you can see how this fabric now will allow me to get from one Aries to another Aries inside the same group in 2 hops. It would be the minimum number of hops in general. I can go across a green, and then I can go across a black. Clear? All right. Now, coming off of the Aries as well, we say, well, we have the optical cables coming off of every single Aries. Now, we're going to talk more about this in a minute, but it's important to note right now that, well, coming off of pairs of Aries are the optical networks, and that's what's going to implement the rank 3. So we don't need another set of routers that we need to communicate with in order to go across the opticals. This is the opticals will plug directly into these routers, directly into this mesh. This is what it looks like when you actually build everything up, but take off the back skins. And it looks pretty crowded, but at the same time, it's all pretty well orchestrated. So behind all of these wires on slide 14, behind all of these wires are the chassis, the compute nodes, and the PC boards. You don't see any of the compute blades here or the rank 1 network. But what you do see is everything that's plugged into that backplane, and that's the copper cables. Now, these are actually black but color-coded, and if you kind of follow them, you can see how you have a group of, a group of, there should be 3 here, that are running from this chassis, running across another chassis in the other cabinet, or another chassis in the same cabinet. And they crisscross, and you can pretty much convince yourself, yeah, that does sort of look like an all-to-all between the cabinet, or between the chassis of the 2 cabinets. In this case, colored green, the fiber optic cables. They, again, plug into the same backplane. They don't need to communicate with anyone else. None of the fiber optics doesn't handle any of the communication that stays within a group. So all of them just plug in and immediately go up and out the top of the cabinet. And they actually run in trays to the other cabinets and then go back down, and they're connected on the other side. But that's what it looks like kind of physically as you take off the skin, and you can kind of see it. So now the routing. I've hinted at this a little bit with the rank 1 network, adaptive routing. Now we're going to see how adaptive routing works on the group level, which is both rank 1 and rank 2. Slide 15, we again have our 6 chassis. Each chassis has 16 Aries. And we have one Aries marked S as the source of our message, and one Aries marked D as the destination of our message. So how would a packet go from the source to the destination? Well, we have this concept of a minimal route. The minimal route is to take one green hop to an intermediate Aries, and then one black hop to the final destination. Now, the green hop in the minimal case, the green hop takes you to the intermediate Aries that's in the same column as your destination. And the packet has enough information that it knows what Aries that is. So it can jump once, jump a second time, and boom, you're at your final destination. The routing rules actually say that you have to do a green first, and then you have to do a black. So there's only one minimal route between these any 2 points in the same group. But there's an alternative, and what we call a non-minimal route. Okay, and the non-minimal route is, again, it's very easy to overwhelm the minimal route. It's very easy to overwhelm any single wire in the system. So it can choose, depending on the mode, but in the mode that actually the machines are in production, it can choose to send it a non-minimal route. And in that case, what it does is it does one green hop to a intermediate Aries, a black hop to and another Aries, which we call the root Aries, and then from the root, we again do a green and a black to the final destination. Now, for all intents and purposes, you can think of this root Aries, this middle Aries, as being randomly chosen within the group on a per packet basis. So every single packet could be bounced off of any other Aries in the system if you're going off Aries. And in fact, if you have a very large message at all, there's a very good chance that at least one packet of your message will hit every single Aries in a group. So again, it's not the speed of a single wire, it's all of the wires in the system that add up to provide us the bandwidth. So how are these paths calculated? Well, the minimal route is relatively easy to calculate. When you have something in the packet and part of the packet, and it knows where its destination is. And so it says, well, I know my destination is, I follow the rules associated with the routing. And like I said, actually in this case, the rules mean you must do green and you must do black. And that limits your subset. But inside the Aries itself, it's watching these wires. And it's watching how busy the different wires are. And it can actually choose, what it does is it chooses a minimal, and then it looks at a couple of non-minimal routes. You can say chosen at random. So a couple of non-minimal routes chosen at random, and then compares the minimal to the non-minimal route. And again, depending on settings, but the normal setting is no bias. So depending on the how busy the different routes are, it will say, well, I just choose the non-minimal or I choose the minimal.
So source Aries is doing
this. This happens at every single jump. So it happens right here, and if it decides to do the minimal route, it will happen again here. Even though you're here, it doesn't have to take this route. It can actually jump off this and go there again. So as you move through the network, okay, the number of choices is narrowing. But at every single step, you can choose to go minimal or non-minimal. You can choose to do adaptive or not. Now, the exact algorithm for choosing the adaptive route is more complex than random. But for all practical purposes, it's just easiest to think of randomly picking one of the minimal routes. It can't quite choose, it doesn't look at all, 15 possibilities simultaneously. There's a down select, and then it chooses. But even then, the down select process is pretty much going to scramble your message across the whole group. Now, this is what happens inside of a group. This doesn't communicate outside of group, and the optical cables are not involved at all yet. Yes? Yes, absolutely. If your destination is in the same chassis, it can choose to go to a non-minimal route, go to another Aries, and it doesn't have to immediately go to the same green. I'm not even trying to think if it's biased towards that at all, again, but I don't think so. I don't think there's any rules. It can bounce off another chassis and then come back. Now, you might think that's a little bit, it's taking more hops than necessary, but really the philosophy behind a Dragonfly is to spread these things to the wind so you don't have hot spots, or that if a hot spot ever starts to form, you're immediately routing around it, and you use the power of all of the wires. So yeah, even if you're inside the same chassis, doesn't necessarily mean your packet is going to stay inside the same chassis. Now, if you ask the question, if you're inside the same group, it stays in the group. So just if your source and destination are inside the same group, the optical network is not involved at all. And that's why we can draw a relatively nice picture here and just talk about what's happening inside of a group. We don't have to worry about the optical at all if both the source and the destination are inside the same group. So, like I said, adaptive routing, we select between minimal and non-minimal paths based on load. We actually select between non-minimal paths based on load if we choose a non-minimal route. But the important thing here also is if you actually kind of calculate up all of the wires, all of the speeds of all the wires, the class 2 group, that's the configuration that we call this 2-cabinet group, has sufficient bandwidth to support full injection rate for all 384 nodes with non-minimal routing. What that means is that every single blade, every single compute node on every single blade of this group can be injecting data simultaneously, and in theory, and we believe in practice, there are enough wires and enough bandwidth that even if every single packet takes 4 hops, non-minimal, we can sustain maximum bandwidth. So it takes some getting used to, but this is the kind of remarkable thing. And if you go back to the XE system, there's a lot of wires there, but since there was no adaptive routing, and it was if you go from point A to point B, this is your route, it actually turned out that a lot of the wires were sitting idle a lot of the time. The philosophy is that, well, if the wires are there, we're going to use them. And we're going to have enough wires to handle all of the load simultaneously if you try to push the system that hard. Yes? The rules are such, I say up to 4, because the rules are such that it must get there in 4 routes, in 4 hops. And that is because when you choose, let's go back to the source right here. If you choose a non-minimal route at that point, okay, it can take 1 green hop. After that point, green is no longer a choice. And so it must take 1 black hop. After that, it hits the root process, or it hits the root Aries. And at that point, it must take a minimal route towards its final destination. A minimal route is only 2 hops, a green and a black. And so you are guaranteed that this thing will bounce, or will get from the source to the destination in a maximum of 4 hops. It's not allowed to bounce around the machine indefinitely. At least not with these routing rules. One could imagine another one, but we won't get in there. But so yeah, we can put an upper bound on the number of hops that it takes. And actually, if we're ever asked to calculate the latency of a system, we just assume the upper bound in terms of the number of hops. Now, I will also say that these hops are really fast, and it doesn't take very long to transverse the hops of the system. And actually, from what we've tested, a packet can travel between any 2 Aries in an entire system, including the optical, about as fast or faster than it can go from the Aries across the PCI network to the processor. So just getting off the compute node takes more time than it takes to cross the full system, even doing multiple hops, non-minimal routing. So it is pretty fast, these hops. Okay, any questions? You know, I want to make sure everyone's okay here. This is actually pretty important, this concept of a group. How big is the group? And if I am routing between points, if my source and destination are inside the group, the individual connections aren't what matters. It's the whole group that matters, and they're not using the optical at all. Right. So that is a good question. Is it important from a programming point of view? It is an interesting question about placement and how is your job placed, and then do you have to code anything different if your job is placed different? I would say right now it looks like the placement algorithms that we have, well, they tend to put a natural order for your application. It fills up a group and then moves on to the next group. So if you're communicating with PE rank +1 or -1, well, it's probably on a node, but on the same node. But nonetheless, even if it, +10 or -10, then it actually turns out that there's a very high probability it's going to stay within a group. Now, you can kind of ask yourself, well, if my communicator is contiguous in a subset of the larger machine, there's a good chance that what's in that communicator is going to stay within a group. I say good chance because it's not guaranteed. It depends on the placement. But that is one thing that we're kind of looking for and wondering, does that matter? Now, the other thing is does it matter? Well, it depends on the optical network. If the optical network is powerful enough, then that doesn't even matter. But we're kind of watching to see when that happens or how often it happens. But a general rule of thumb is if you're kind of communicating with an MPI rank that's relatively close in logical space, there's a good chance you're communicating with it relatively close in physical space, and it's staying within a group. And that's basically the basis of a supercomputing paper, which I'm trying to write right now. So. And if we have time, not today, but I'll talk. You can actually see something similar on a 3D torus and on a node. And there's a 3D FFT example that I have, which might be interesting if I have enough time. So that was what we spent up to now is inside of a group, a chassis, and then built up multiple chassis to build up a group. Now we're going to talk about the rank 3 network. Again, we have an all-to-all pattern, but this time it's between cabinets. So take everything in a group and just lump it together and think of it as one big entity. Okay? Stop thinking about it in terms of having whatever number of Aries in it, 16 times 6 Aries in it, right? Think of it in terms of one large group. And there is an all-to-all pattern wired between the groups using optical cables, what we call the blue network or the rank 3 network. This global bandwidth can be tuned by the site, but it's basically tuned by the site upon when they order it, right? This isn't something you tune on an application level. And what we have here on the bottom is a 7-group system. Now, if I click it once, we have an all-to-all. And I think if you follow the blue lines, you'll see that there is one blue line connecting every single group to every single other group. Now, these blue lines actually represent what we sometimes call bundles. And the size of the bundle is dependent on how many how many optical wires you buy. And the size of the blue wire is actually also dependent on the number of number of groups that you buy. And we have all of these configuration schemes that say, well, how do we actually cable this up if we have X number of groups and Y number of cables? So if we look at adaptive routing over the blue network, I don't have a fancy red dot on this one. But again, I'm just going to have a 5-group system represented on slide 17. And I'm going to say that the communication is trying to send a message from somewhere in group 0 to somewhere in group 3. Now, let's imagine that if it's not just one node, maybe it's a number of nodes that are trying to send a number of messages from group 0 to group 3, all at the same time. So we can assume that the minimal path between 0 and 3 becomes congested. It's actually relatively easy to cause this situation. It depends on the actual configuration of the machine, but it's certainly plausible to imagine it. So what happens? Well, again, traffic can bounce off any other intermediate group. So it can go through 4 and then to 3, or 1 and then to 3, or 2 and then to 3. You are limited, getting back to your question about the number of hops, right? You're not allowed to just bounce around the machine indefinitely. You can only bounce off of one intermediate group. So you can't go from 0 to 1 to 4 to 3, 2 to 3. You can't do that, right? You can bounce it off one intermediate group and then the other. And again, for all intents and purposes, when this happens, you can begin to think that, okay, the intermediate group is chosen at random. So really, when communicating outside the group, it's not so critical to think of it as what's the bandwidth between individual groups, but what is the total amount of bandwidth that's connected to the group that's the source of the message to the rest of the group, to the rest of the system. Yes. So the limit on the number of groups is 482. No, the limit on the number of groups is 241. The limit, that means the limit on the number of groups is 482. Now a group is twice as dense as an XE, so that would be equivalent to, what did I just say? About 800 to 900 XE cabinets. And, you know, Blue Waters is 300. So we're talking about, you know, the limit of this thing is about 3 times the size of Blue Waters. So if you ever want to put in a proposal for that, go right ahead. We're all for it. So we have some practical engineering things that say we'll go less than that. But I'm sure if someone wants to buy that large of a system, we'll figure out a way to build it. So that won't be too big a deal. The point is it's pretty large, the limit, and you know, right now we're in the tens of cabinets, tens of groups as our largest systems that are planned. You know, we really hope that someone goes really tries to push the limits, but we'll see how it works out. Yes. How do you do that? There's a few ways to do it. One very high-level way of doing it, and often the simplest way to explain it, is to somehow look at the number of wires in the system and calculate the peak bandwidth of all the wires, and then say, even if this thing is not symmetrical and I don't quite have a bisection, what's the sum of all the wires and divide by 2 or something like that? Whatever the proper mathematics is, depending on how you do the summation. That is one easy way to do it. A more complicated way to do it is to do that, and that can be thought of kind of as a theoretical global bandwidth. But a more complicated way to do it is like, well, what would be the bandwidth if you did an all-to-all across the system? And there you can say, well, what percentage of the data stays on group versus off? And we have spreadsheets to try and calculate that, that kind of stuff. That if we're really trying to predict the performance of all-to-all, we'll do that and take into account the number of optical links and try and take into account the efficiency of the individual links and try and take into account how many things they bounce, you know, because if you bounce a packet off an intermediate group, you're basically putting twice the load on the optical network as if it's minimal. So that's another consideration. So the easiest way to do it is just to count the number of cables, have you know, add up all of their bandwidth, divide by 2 to say this is some kind of, you know, this is a global bandwidth. I can work with you. I have to redo it every time myself. How many times do I have to multiply by 2 or divide by 2? But that's the easiest way to do it. So, well, you just measured it, right? That's not wrong. That's what you measure. But if you measure it and compare to something that you calculated, yeah, that gets interesting. Your measurement is going to be less than what you calculated, perhaps, depending on your assumptions in the calculation and where your bottleneck actually was. So, yeah, that's what we are often try and do when we predict out systems. That also assumes that you configured the machine such that your optical network is the limiting factor, which most people, that's the simplest assumption because otherwise it just gets even more complicated. But it is very easy to build systems where the optical network is not the limiting factor anymore, especially for small systems. So there's other considerations when you actually do that comparison to keep in mind. Oh, I just said that there, right? So again, the last note is when you do adaptive routing and bounce it off intermediate group, yes, it doubles the load on the network, but the point is that there's a very large percentage of the time that these cables are actually idle. You'd be surprised. I mean, these things are just sitting there idle for the vast majority of their lives, and so why not use them? So that's kind of the philosophy behind the Dragonfly network. You can come up with a few end cases, worst case scenarios, and yes, we try and test those and stuff, but it's really debatable as to whether or not those worst case scenarios will actually happen in a real production system. So here's another picture similar to what you saw before, but this is four cabinets all cabled together. So again, we have the copper connections here, the opticals that are going up, crossing a tray right here, and then going back down. When you have, because it's an all-to-all network, if you were actually to, I didn't see this yet, but if we were to go upstairs and look at the system here, it's not laid out in a regular pattern anymore. We have flexibility. All that matters is they're relatively close, and there's some good reasons to make them in longer lines. But you'll see like a line of 8 cabinets, and then you can have a line of 4 cabinets. You don't have to have 2 lines of 8. That's different than the XE system. XE, you actually had to have a very regular grid pattern in terms of the number of cabinets as well. You can have prime numbers of groups if you want. So now I'll move a little bit onto the Cray software, but I mean the topology is kind of a main point, and it's kind of interesting how things move around. Now, it is, I will say in a way, it's Cray's goal, and it's my hope, that you don't have to think about this very much. But people want to know it and want to know what's going on behind the scenes a little bit. But ideally, you kind of log onto the system, your job gets placed, and you don't have to think about placement very much. And that's our goal. So, but it's interesting to know what's happening as it's communicating around the system. Okay, now I'll talk about the Cray software, slide 19, moving on to slide 20. The point of the slide on the point of the material on slide 20 is to show that there is actually a lot common between the XE and the XC. The XE is the current production machine. The XC is the new Cascade system that you'll get access to very soon. So in terms of applications and stuff like that, it's going to be very similar. The software stack on the left-hand side is the XE. Software stack on the right-hand side is the XC. Challenge you to kind of find where they differ. It's like, well, there it says Gemini on the left-hand side, and there it says Aries on the right-hand side. And then all of this is the same. All of this is the same. Very right down at the hardware extraction layer, there's a little difference between Gemini and Aries. Even that is really pretty similar. So this is a very good news for Cray because it doesn't mean that we had to have a brand new software stack, right? It's very similar. A lot of the stuff just moved over. MPI, for the most part, moved over wholesale. I mean, it was just a recompile sort of thing. And you didn't have to redo anything. Now we're tuning MPI, but getting it over it was just a recompile. That really helps. Same thing for applications. You know, when we first started getting access to the Cascade system, access was very limited, and so we actually said, oh, well, we get lots of codes in from other places. So the first thing was to get it running on the XE system with the compilers that you wanted to use on the eventually on Cascade, and then move it over to Cascade, recompile, and run. And if you were already using the compiler that you wanted to use on the XE system, moving it over became very simple. So that was very positive experience for the benchmarking group as well, and something that we hope this community sees in general, that they can port things over very quickly. In terms of the programming environment, what's available, actually this, again, looks very similar to what's available on the XE system. For programming languages, we have Fortran, C, C++, Python. Python, I really think this is on the login nodes. I don't really know if Python is used too much on the compute nodes, but I suppose you could in a couple of modes if you wanted to. For programming models, the distributed programming models, it's dominated by MPI, but you also have the PGAS languages, SHMEM, UPC, CoLRay, Fortran, which is now Fortran 2008, Chapel, if you're interested in something a little bit more out there. Shared memory programming, we have OpenMP, OpenACC where applicable, but OpenMP, you also have pthreads if you want to do that. So the programming models are very similar. Compilers, the Cray compiler is the one that's going to be over there. GNU is obviously there. One difference, I don't know what's available on your XE system, but PGI was available, and for a while the default compiler on the XE. PGI is no longer available on Cascade system, but the Intel compiler is. And I'm not too sure, is the Intel compiler going to be the default on your system? Don't know yet? Or you don't have a default? Okay. Okay, so you can. Okay, so it's, and we'll talk about this more later on in the week, but basically you choose by loading the programming environment associated with whatever compiler you want to use. Tools that are available, debuggers and performance analysis tools are the same as what was on the XE system. Libraries, Scalapack and BLAS. Oh, I shouldn't have libgoto there anymore, because libgoto, Goto was unique to AMD. Now the Cray libsci is based on our own internal base software, but we also have MKL, which is the Intel-based BLAS. And then I/O libraries is NetCDF and HDF5. Another picture of the same thing, sort of. Compilers going around the universe here is compilers, debugging, performance tools. Job management, there's a few different job managements. This site uses Slurm. I think you'll learn a little bit more about Slurm and a couple of the hands-on things. And then applications, if you are interested in ISV applications, there's a growing list of ISV applications that are available. So the Linux environment, we really have the focus of this environment is performance, stability, and scalability. Now, scalability and performance, you can say, are two sides of the same coin, really, because a lot of the scalability and performance at scale comes from the scalability of the system in general and low noise. So we have lightweight operating systems. We are based on the standard environment, but for the next slide, I'll talk a little bit more for the native version. We strip out a lot of daemons and strip out a lot of the noise to have it scale higher and perform better. But then we also, as we scale up machines, we find lots of either defects in the operating system or defects in our own software, or perhaps bottlenecks that were never considered before, and we try and fix those and correct those as we anticipate them or as we find them and scale up the system. So we have this thing called Cray Linux environment. That's CLE is what we call the operating system in general. We use Linux as the foundation because Linux has kind of become a de facto standard again. It's people know how to use it in our community. They're familiar with it. It's solid, robust. But we have two modes. Now we have what we call extreme scalability mode, native mode. I would actually say the default mode. If you just log into the Cray system and you compile and then you run an application that has been recompiled for that, you are using extreme scalability mode. This is no compromise scalability. Like I said, low noise kernel. We tried to minimize the amount of noise in this kernel to allow for greater scalability. Native communication, if you're using MPI, you're linking in the Cray native MPI to use the fast communication mechanisms across the Aries system. And then you've tuned your performance and looked at our debuggers and stuff like that. This is all of the extreme scalability mode. However, not everyone is willing or able to run in this mode. And the classic example is ISVs. So we have a cluster compatibility mode. Now, I don't know if anyone in this room will really use this very much, but it's important to know that it's out there. Cluster compatibility mode is basically no compromise compatibility. What it does is at the time of launch, it turns the node into a full standard x86 Linux with standard communication layers. It's supposed to be, out of the box ISV installation. If you get some binary from an ISV, download that binary as long as it's x86 binary that's supposed to run on Sandy Bridge or whatever. It should be able to run in that mode. Now, I am not sure how that works with Slurm yet. It doesn't. So it's a work in progress, and everyone can put pressure on Slurm to make it work, and probably that really means is put pressure on Cray. Now, but it's important to know that the capability exists out there, I think. So if you foresee the need for this, then you should also be, letting this site staff know so they can put even more pressure on Cray. Mm-hmm. Yeah, that's the only way we run inside of Cray. I mean, cluster compatibility mode is even available on our own internal machines, and if anyone is doing ISV application testing or something like that, that's the only way that they can run during batch time is via that mode. So, not even during batch time, during any kind of time, that's how they do it. So, I'm not an expert on the syntax on how to make that work on even other workload managers, but I know it's done on a pretty routine basis. A few words on storage, just to give you a feel for actually what's out there. Storage is actually, we have this deal now with Zyratex is the company. The product is called the Synexion. It's great. They basically randomly put letters together to come up with a unique name that's not trademarked. So It's called the Synexion. It really has three components. One is the metadata module. This is the metadata, I think of that is what's controlling like the creation and deletion of files and where they are, creation and deletion of directories, not really doing the writing of the files, data to the files or not. Did it just switch? I didn't think I put it. Okay. So the next one is a scalable storage unit. This is, has the storage controller in it. It has all of the disk and the disk controller in it. I can't even remember how many disks it's got in there, but it's got a lot of disk in there. It's what implements the RAID is in there. It's really a completely self-contained unit. And you buy multiples of these to build up more and more capacity and more bandwidth. Then you've got the fully prepared rack, and this rack is wired so that you can put in a maximum of 6 SSUs, scalable storage units, and 1 metadata unit. Now, every rack doesn't necessarily need to have a metadata unit, and every rack doesn't necessarily need to have 6 SSUs. This is all configurable based on how the site actually chooses to lay out their file systems and the number of SSUs they want. And some sites are even on power and cooling constraints. So it's really, the SSU is supposed to be a scalable unit. That's how you decide, okay, when someone comes to us and we want this much capacity, when we want this much bandwidth, we decide, we kind of help them figure out which one is your limiting factor and then build up the file system. The next slide is just, well, we have the metadata controllers. On the Synexion 1600, that used to be the 1300, now we're going to 1600. They enhanced the metadata controllers. They enhanced individual controllers in the SSUs. So we should be able to push the SSUs faster now than on the 1300, ideally greater than 5 gigabytes a second. And the metadata controller should also be faster. But your ultimate speed is really dictated by a parallel file system and the Lustre file system. I'm not going to today, or I don't know if this week we're really going to get into, I/O performance and how to do that. But it is a Lustre file system, and doing parallel I/O to lots of different stripes is the way to get performance. A few words on benchmarks. This is pretty high level, but it's going to give you an idea for where your codes are going to be faster or slower. So what I did, it's kind of difficult to do a direct comparison always because between two machines, because a lot of things can change. But what I did is I ran a typical XE base with Interlagos inside and XC with Sandy Bridge. Typical. Really, actually, this meant what I had access to inside of Cray. But I used, for various ranks, I used between 256 and 512 compute nodes, depending on what I had available and what data I had. The actual results will depend on the actual system size, but this is a high-level stuff, right? So one thing is HPL. Now, I describe this in terms of percentage of peak because these two were running at different gigahertz. But I think it's interesting to note that actually the percentage of peak is higher on Cascade than it was on the XE. And this is something that we do see. So we're getting, this is dividing one column by the other column. So XC is faster, if you will, given a fixed gigahertz. Why is that? Well, if you look at the star DGEM number, the Cascade actually goes a little bit faster than peak. How was that possible? Well, peak is often calculated or quoted by, the number of flops per clock times the clock rate. Well, these processors aren't running at the clock rate that they say they're running at. Right? They're constantly fluctuating their clock rate. Now, we'll see what Intel says about that tomorrow. I'm curious to see if they talk about it very much. But from my perspective, they are somewhere around that gigahertz. I can't remember, I can't even remember myself as to Is the quoted one a floor or is it a ceiling? I know it's not the ceiling, but is it a floor? I don't remember that. So be careful a little bit about putting too much faith into, oh, I'm running at 2.6 gigahertz. You're running at about 2.6 gigahertz, right? You might actually be running it faster than that at times. I can't remember if you can run slower than that, but it doesn't matter. I love, think Heisenberg uncertainty principle. You really don't know how fast it's running. Streams is another one. This is gigabytes per second per node. This is not a percentage thing at all. Comparing Interlagos to Cascade, we see that there is a slight, 8% improvement on the total bandwidth available to the node. This is all cores firing simultaneously to their local memory size. It's a slight increase. I'll take it. It's not a doubling of the speed, though, from Interlagos to Cascade, but nonetheless, I'll take it. Random ring bandwidth. This is something with random ring. You're basically, it's forming a ring of communication, and you're communicating with your neighbors in that ring. But since it's a random ring, your neighbor can be anywhere in the machine. And in fact, this begins to act more like a global bandwidth test than a nearest neighbor test. And here, as we start seeing the advantages of the Cascade system, this is like 2.5 times faster on the random ring number. And I think we're actually trying to see if we can push this number up even higher. Point-to-point bandwidth. I give a range for the XE system because really, even if the machine is idle and you're only communicating between point A and point B, the speed which you observe the bandwidth between point A and B depends on where A and B are. So if they're very close together or they happen to take the right path, the bandwidth you will see would be higher than 5 gigabytes a second. But it's very easy and, in fact, very likely that the farther you are away, that you're going to see bandwidths in the range of 2.8 gigabytes a second. Where on the XC system, the bandwidth doesn't matter. Again, remember I said there's adaptive routing. It doesn't matter if the minimal path is, you can overwhelm the minimal path. It's the aggregate. So really, as far as anyone I've ever heard tested, if you take any 2 points in the system and the system was idle and you can do a point-to-point bandwidth test, you're going to get greater than 8.5 gigabytes a second. Nearest node point-to-point latency. Nearest node is something that we often are asked to quote in systems. Nearest node in a 3D torus meant something. I think it meant one hop in any one of the 3 directions. It's a little less confused, a little less well-defined in a 3D torus, perhaps, or in a dragonfly, perhaps. But we defined it at 1 green hop away, and we say it's less than 1.4 microseconds now. So we did improve it some. I believe that this wasn't our biggest problem here. This already had pretty good latency. And if anything, latency only became a concern as you grew the system size. As you grow the system size here, this latency really doesn't go up hardly at all. The Dragonfly, we didn't talk about this before, but if you calculate the non-minimal paths of a full Dragonfly, no matter the system size, the maximum number of hops is 10. And so it doesn't grow beyond that. And really, physically speaking, it doesn't matter very much because the speed of light in those optical cables is still pretty small. Speed of light is pretty high. The amount of latency added by the optical cables is not very big. So really, this doesn't climb very much at all, no matter the system size. Now, the 3 at the bottom are various forms of something that either drives small message rate in terms of GUPS, that's a PGAS single word test, and then the other 2 really drive all-to-all type of communication with larger messages. GUPS, in the case of GUPS, that's a 5x improvement on the same using the same number of nodes. In terms of GFFT, which is a one-dimensional FFT with an all-to-all across the machine, you can basically think of it as dominated by all-to-all. That's a 3 to 4x improvement, and really, if you look at this, it would be higher, except for now compute is becoming a substantial part of your time again. So that's interesting. On the XE, the all-to-all really dominated. On the XC, it's much more in the range of kind of 50-50. Hammer sort is another one that's kind of interesting, and again, a 4x improvement. That's again a global bandwidth type of stuff. If you have global bandwidth codes that are very intensive, we're going to see not a 10% improvement. We're going to be seeing and shooting for 2x improvement or more. And on Wednesday, I'll talk a little bit more about kind of what you see going from Interlagos to Sandy Bridge. Or Magni cores from Sandy Bridge if you're used to that one. So this is WRF data. WRF is a weather research and forecasting model, classic 2D decomposition, mostly nearest neighbor type of communication. We just like this line because it's above all of the other lines, including IBM, and it goes pretty high and it scales pretty well. So with this thing, the combination of Sandy Bridge being a faster processor and using 16 threads per node means it's going pretty fast with fewer cores. And then on our network, it's scaling pretty well. I think as it gets out to here, it's just simply running out of work because this is strong scaling, not weak scaling. This is something that I'll whet your appetite with or give you something to think about. This is a CFD code, and rather than really look at the exact times, the interesting thing here is that the lower is better, and these are the number of cores, but it's interesting, the ISV community really thinks the Interlagos node has 32 cores on it, and really thinks the Sandy Bridge node has 16 cores on it. And we'll talk more about whether or not that's really true, but so when they say 512 Interlagos cores, well, that's using 16 nodes, but the same 16 nodes on the Cascade is 256 Sandy Bridge cores. And using the same number of cores, it is faster and it's using fewer cores. This is important to some people if they really want to go the maximum speed with using fewer cores. You can get you can create graphs that really look very nice if you plot it on a per core basis. Another one here is a number of cores again, and again it got shifted down using a down is better in this case. Using a same number of cores. It goes out twice as far on the XE system because really these two are using the same number of nodes. So even using the same number of nodes, we're faster, but if you look at it on a per core basis, we're faster. Something to start thinking about, and we'll revisit it. We'll see what Intel says about using hyperthreads or not using hyperthreads, and we'll revisit this again on Wednesday. Wednesday, Thursday morning, both, one or the other. So something like that. And with 2 minutes to spare, that is the end. So if you have any questions, you can I can back up to anywhere in the slide deck now or just answer them. The cables themselves are really pretty thick, and they don't go very far. Those are the two cons. In this case, we're talking a few meters in distance is where they really can live well without needing repeaters or slowing down. So the rank 2 network is using passive coppers to communicate between cabinets. And the total distance, I think, is going to be something on the order of 3 meters or less by the time the cables are coiled around. Then we have a rank 3 network, and that's active optics. Active optics, fiber optics, what's being transferred is light. This is a very low latency, no matter the distance of the optics, and the cost of the optical cable itself is not strongly dependent on the distance it needs to go. So this really frees us up to have cables that are very long. The thing that makes it the most expensive, though, are the endpoints. They cost more. The actual endpoints cost more to hook up to machines and to get the bit rates that we need. So it is something that we don't want to use throughout the machine, but we want to use it where it has its advantage, and that is communicating between what we call groups, communicating between pairs of cabinets. And furthermore, the number of optical cables that you can get in an XC30 is actually dialable by the site. You can choose to connect in more or fewer. So that's going to help us optimize the cost of the system, so you're kind of putting the money where you want it. If it's in the network, if it's in a global network, you can buy more optical cables, or if you don't think you'll need that many, you can buy fewer, and that'll free up money to buy more memory or more boards. So the next thing is a very large increase in global bandwidth. This will be a theme on a couple of things this week. The Gemini system was a 3D torus. It was good in a lot of ways for bandwidth, but 3D torus don't necessarily scale quite as well as some people like in terms of global bandwidth if you're doing an MPI all-to-all across the machine or whatever. And so this actually provides a massive increase in global bandwidth. Now we'll give a range because really the exact increase depends on the size of the machine and in configurations and whatnot. But it is really going to benefit codes that do all-to-all, do searching, adaptive mesh refinement, higher order nearest neighbor, the 3D and 4D type of nearest neighbor codes. If your codes do a lot of communication, that's where it's going to see some benefit. We also have support for some collectives, barriers, and all reduce. Okay. That's okay. Yeah, funny faces. Over to my right is the entertainment, right? So we do have some hardware support for collectives. This will speed up a few things about barriers and all reduce if you do those with the really high frequencies. The interesting challenge there is that many times when we see barriers taking a long time, we're always going to ask ourselves, is it because the barrier is taking a long time, or is it because there's some type of imbalance in the code, and it's whoever is getting there last is the result to what's causing it to take a long time? So that's going to be an interesting thing to watch. We do increase the size or the rate at which we do small messages. If you go way back in history to the machine previous to Gemini, actually, that was pretty good at some things, but it actually was pretty poor at message rate. We had a massive increase in small word message rate going from that machine to Gemini. Well, so we didn't need as large of an increase going from Gemini to Aries, but we still improved it, in this case, by about 3x. And then the PCI is our new interface to the processor. This benefits us because it makes us less dependent on processors going forward. They should be able to connect up to anything that talks PCI in the future. So really the philosophy behind the network is we use the right mechanism to transfer bits at the right level for the cost. We're optimizing cost in terms of, well, if we're transferring it over this distance, this is the best way to transfer the bits. And so starting at the left-hand side, we have this concept of what we call a rank 1 network. The rank 1 network is communication through a PC board. And I don't know really what the units are, but the point is that you're transferring it for pennies. It's really relatively cheap to lay down wires and to get bandwidth over this level. Now, a PC board, you can't build a PC board that spans the machine room. This is the size of what we call a chassis. So something less than a meter is the distance that this is transferring data over. The next level is what we call a rank 2 network. Passive copper is what that is. Now, copper is really good in a couple of regards. You can have pretty good signal rates in it. It is really relatively cheap, but we'll go into differences in speed and bandwidth. But the signaling rate of this is a little bit higher than the signal rate of these. But we'll actually see, hopefully, at the end of today, really what matters is not the speed of an individual cable, but the speed of the aggregate system. So these are our building blocks. We start with a compute blade. A compute blade has actually 4 compute nodes on it. Each compute node has 2 sockets. We'll talk about a compute node in a little bit. But this is really the smallest physical unit that goes into the system. They all connect up to one Aries card that then communicates with the outer world. We put 16 compute blades together into one chassis. And this is pretty densely packed when you get it all together. And they all plug into one backplane. And you can, this is an engineering diagram, but nonetheless, you can see this green-black backplane. That is the rank 1 network, and that's what implements the rank 1 network, which we'll talk a little bit more about its topology in a moment. Once you have a full chassis, you put multiple chassis together, 3 in one group, and then three in one chassis, 3 in another chassis, to form what is called a group. Now, that group is tied together with the rank 2 network that I talked about, passive electrical network where the cables are basically running between the chassis. All total, by the time you get up to 2 groups, that's 384 compute nodes, 700 and some sockets, right? Now, a rank 3 or a full system is cabled together with the rank 3 system. If we have the opportunity, hint, hint, to go upstairs and actually look at see the system through the window, you'll actually see it. Yes. All right. So my name is Nathan Wikmann. I work at Cray back in the performance analysis team in Minnesota. I do a lot of different things, wear a lot of different hats about benchmarking and whatnot. Today I'm going to be talking about the XC30 system in general that was previously codenamed Cascade. So if you hear me say Cascade, I'm talking about the same system here. It is a lot about the network, so we're going to be spending probably a little bit more time on the network. And the network is quite different than anything out there before. So feel free to stop me, ask questions. The more lively this group is in asking questions, the more fun it is for me and for everyone else. So don't hesitate to interrupt me or challenge me on a couple of points. Jeff said that he was going to try, so we'll see how he does. We're going to start off today talking about the Aries custom interconnect. It is custom. We do the network ourselves. We do the network ASIC ourselves. And then all the fabric is our own fabric as well. why are we doing this and what is the difference between Aries and Gemini? Gemini is the router chip that is in the XE30, the current production science machine here, and the product that we've been shipping now for several years. Well, the main differences are a 3x increase in the sustained injection bandwidth. So we're changing the technology. Gemini was based off of hypertransport. This is now moving towards a PCI connection, and it actually provides better bandwidth in general going across a range of applications. We have also